Raman spectroscopy. After I shot this video, it's now one of my favorite analysis methods. Today we are at Dr. Lentin's lab to carry out and explain this analysis method. Here's a quick summary. The Raman effect, which is used in this method, works as follows. A laser beam is shot into a sample and a tiny part of it collides with the matter, changes the vibrational states in the compound, and then the inelastically scattered light, i.e. the light with now less or more energy, can be measured. At first glance, this sounds a bit like IR analysis, but there's a few important differences. In Raman spectroscopy, a bond is visible when its polarizability changes during its vibration due to the interaction with light. With IR, it's the dipole moment. The best example is the CO2 molecule. We have 3 vibrational modes, but only 2 of them result in a change in the dipole moment. This vibration does not, but there the polarizability changes, i.e. how easy it is to shift a negative from positive further away. Less attraction, more easily shiftable. This bond is then visible in the Raman. In contrast to IR analysis, monochromatic light, so light with exactly one wavelength, is used to cause this excitation. This means that we have to choose between 3 different lasers. With IR, you simply pass a bandwidth of the IR spectrum over the bond in hopes that there is one wave number that excites the bond to vibrate. In Raman analysis, the light is scattered and not absorbed by the molecule as it is with the IR analysis. So here too, there is an important difference from fluorescence analysis. In fluorescence too, the photon is absorbed and excites a very specific state, and then the system falls back from the defined state to the ground state with a specific lifetime. We do not have defined states in Raman analysis. With scattering, we can excite more or less any virtual states in terms of energy. So Raman is also a form of vibrational spectroscopy, but one that uses light scattering. With scattering, we have Rayleigh scattering and Stokes scattering. In Raman analysis, we use precisely these 2 Stokes scatterings to obtain information about the bond. With Rayleigh scattering, you don't get any information about the bond. In practice, normal Stokes scattering is used more often. Anti-Stokes is also used, but we want to take a look at the device, don't we? So now let's take a look at the device. Where does the light come from? Well, from these lasers. In this case, 3 different ones are built in: blue, green and red. Green is the standard because it's a good compromise of not too much energy, but it still covers a broad range that is of interest to mineralogists. The red one would be important if fluorescence occurs due to the excitation with green lasers. Through a few lenses and mirrors, the monochromatic green light hits the mirror, which directs the light via further mirrors through the microscope and then into the sample. Then something amazing happens. A chunk of light is simply scattered elastically. This is called Rayleigh scattering. This light does not provide us with any kind of information and simply overloads the measuring electronics. A tiny fraction of the light loses some energy via inelastic scattering, i.e. through the excitation of molecular vibrations, and is scattered back with less energy. All the lights come back again. The Rayleigh filter filters out the elastically scattered light from the laser, which has simply remained too much. This means that no more laser light, but only Raman radiation reaches the detector area. There's another mirror there, which directs the Raman light into the grating. The grating works like a prism that spreads the Raman light into a spectrum. Depending on the grating, you can also scan the spectrum a little bit more precisely. The detectors are these 2 there. The upper one is for fast readings and the side one has a better noise to signal ratio. Both of them are CCDs cooled to -50°C. The sample you want to measure goes on this stage. And what can you put on as a sample? Actually, anything. Liquids, gases, solids. Maximum height is about the width of your hand. And you can also use a plate like this to heat or cool your samples during the measurement. To do this, the sample is placed in there and then screwed shut. This means that you can also fill this chamber with inert gas or measure it at a certain humidity. I simply used a crystal which I found during another field trip as an example. Well, I'm quite certain that this video will come up before the actual field trip. Before taking any measurements, the laser needs to be recalibrated against one of the internally mounted silicon crystals crystals. Once the optical focus has been set, the laser itself can be refocused. So how do we go about acquiring the spectrum? For minerals, a Raman spectrum covering a range of 99 to 1877 wave numbers is usually sufficient to reveal all the bands of interest. Under the measurement parameter, we essentially configure how much energy is directed into the measurement and for how long. In this case, we'll set it to 1 second per measurement for an unknown mineral. It's a good precaution to slightly reduce the laser power to avoid burning away parts of the crystal. The system will now record this 3 times. This specific setting is actually quite important, and here's why. If cosmic radiation happens to interact with the detector during that 1 second measurement, a very sharp peak will appear. By recording multiple scans, in this case 3, you can easily have the software automatically filter out such anomalies, because that specific event is highly unlikely to reoccur during the other measurements. And now hit play. Okay, the noise level is still relatively high, and the sample can certainly handle more laser power. That is, more laser energy. And now the spectrum looks significantly cleaner. With just a few clicks, the background signal can be subtracted. All of these parameters can be adjusted manually as well, though that isn't particularly important when you're just starting out. The internal library is, well, let's just say okay at most. And since we already know what this sample is, we're better off switching to a different software program that features a more optimized library. In that program, we can perform a much more thorough analysis of the data file, which was saved in a text format. There are 3 different methods available for doing this. During the peak correlation process, the software scans the spectrum to identify and recognize peaks. It notes their specific locations and cross-references them against its database. Based on the green color coding and the multiple of matching indicators, it is already evident that this sample is likely to be a Hawaiian. However, for confirmation, one typically overlays a reference spectrum onto the live data, and it's indeed a Hawaiian that I found. An important note is that certain bands, for instance, are visible only when the crystal is in a specific orientation. This means that even if you're certain of the mineral's identity, and even if the spectrum you've captured shows a majority of the bands in their correct positions, a specific band, such as the one at 1000 wave numbers in zircons, might remain undetected simply because the crystal is misaligned under the microscope. In such cases, you simply need to rotate the microscope slide by 45 degrees, and then the missing band should reappear. The beauty of Raman spectroscopy lies in the fact that virtually no sample preparation is required, and the sample itself remains undamaged. It is therefore a non-destructive analytical technique that can be effectively utilized at the very beginning of an analytical workflow. It allows for the determination of various properties, including crystallinity, chemical composition, doping levels, and even temperature. Higher temperatures result in increased molecular vibrations, which in turn alters the Raman scattering patterns. It is also possible to analyze fluorescent minerals. However, this typically requires switching to a different lasers, specifically the red laser, which must first be allowed to warm up for about 15 minutes. Furthermore, the degree of hydration of a compound can also be determined, whether for a chemist it's a trihydrate or a tetrahydrate, or in the context of mineralogy, whether the sample is calcium sulfate dihydrate, hemihydrate or anhydrate. These represent 3 distinct minerals: gypsum, Basanite and anhydrite. However, it is not only chemists and geoscientists who can benefit from Raman spectroscopy. Biologists and medical professions can also make effective use of this analytical method. In my opinion, it's a fantastic device that I will hopefully from now on feature quite regularly in my field trip videos. For example, when I come across an interesting looking mineral. With that, a big thank you goes out to Dr. Christoph Lenting, head of Raman spectroscopy in the working group for mineralogy and crystallography at the University of Cologne. And of course, a big thank you goes out to my Patreons for the financial support. With that being said, thank you for your attention and goodbye.